Hi, this is Jeff from the Ozark Mountains in Missouri, USA. Today, we're evaluating this Amiga 600, which someone sent me to take a look at. It doesn't boot, and a couple of the latches in the back are broken as well. I thought this would be a great opportunity to delve into a troubleshooting series for vintage computers. Now, I've not worked on an Amiga 600 before, but the same processes, the same troubleshooting steps generally apply to all, so we can get an idea of where to start. The first step in this process is information gathering. If you just acquired the machine, did the seller happen to tell you anything about it? If you've had it for a long time and it just quit, was it doing anything funny before that? Any funny noises or smells or things like that? This particular machine was sent to me by the owner to repair, and he was nice enough to provide some information to me about what he noticed and a little research he had done on a possible problem. Then it's always helpful to look for sources of information. Fortunately, with the internet these days, it's a lot easier than it was back in the 90s. You can search and find the schematics in users groups and Facebook groups and all that sort of thing, and all those things are really good resources. I've done that already. I found the schematics for this version of board that's in this machine, so that'll give us a head start. Forums, Facebook groups, and YouTube videos can be great sources of information, but do your own homework and don't replace a part just because some guy on a video told you to. Apply a little common sense. Try to learn how to do some of these basic tests so you can determine for yourself if you really need to replace that part. Well, let's dive in. Now, I asked the owner of this machine to send in his power supply as well, because that's one of the first places we want to start, is taking a look at the output of the power supply and making sure it's within spec voltage-wise, and that there's not too much noise on the output. Here is our test setup. We've got the power supply that the owner provided. This is the dummy load that I made for a Commodore 64 years ago, and I'm just repurposing it to use for this Amiga. This is a set of adapter cables that I made when working on my Amiga 500. I'll put that link up in the description here. And I've got an HP multimeter set up to measure voltage, and I'm using a Siglent oscilloscope to measure the ripple voltage. And we'll see what the difference in readings are between these two devices. Okay, right now the power supply is off. The oscilloscope is set up with 100 millivolts per division. That's in the vertical axis here. I've got the scope hooked up to measure the 5-volt rail at this time, and I've got the 5-volt and 12-volt rails both unloaded, and I'm not loading the minus 12-volt rail for this test. So go ahead and turn the power supply on. And you can see here with our 100 millivolt division, we've got more than 200 millivolts peak to peak here, which is about the most we would want to see. Now I'll put a load, an 1.5 amp load on the 5 volts, and that really jumps up now. Now we're at about 100, 200, 300, about 400 millivolts, which is quite high. I'm going to go ahead and load the 12 volts down now with about a 1/2 amp load, and that brought down the ripple a little bit on the 5-volt line, but let's have a look at the 12-volt line with the scope. Look at that. That is off the scale. We've got more than 800 millivolts of ripple on the 12-volt line with everything loaded. I'll turn off the 5-volt load, and it reduces it a little bit. It's still more than, let's say 200, 250 millivolts. But with the 5-volt load applied, which is where most of the load is going to be, the 12-volt rail ripple voltage is outrageous. I would not want to use this particular power supply on an Amiga. Now, it may be that this power supply is working within its design specifications and Cisco decided to put additional filtering inside the device rather than the power supply, and it just may be that the power supply is not very good. We can very easily see this on the oscilloscope. Let's take a look over at the voltmeter. Now, while this is a very good quality voltmeter, it is several years old and it doesn't have the fastest sampling rate. I calibrated this at work a few years ago, so I know it's in calibration. Right now I have a 12 volt load, but no 5 volt load. And we're reading 12.1 volts on the 12 volt rail, which is fine. I'll turn on the 5 volt load at about 1.5 amps, and we'll see our 12 drops down a little bit, which is still okay. But there's no indication here of the ripple voltage. Now, one thing you can do, if all you have is a multimeter, you can measure on the AC scale, and this will give you some indication of the ripple voltage, but the problem is it's not catching all those really short high spikes, and it's only showing about 8.4 millivolts AC. So this isn't giving us a really good indication of the true state of the power supply either. Now, a more modern multimeter might have a much faster sampling rate and might do a better job at capturing that ripple. Okay, here's our same test setup, but with my Omega 500 power supply. So let's see what this one looks like on the scope. So here we have power switched on. Only the 12 volt has about a 1/2 amp load on it now. And we've got just a little bit of ripple on the 5 volt signal. It's maybe 40 or 50 millivolts. It's very tiny. I'll put about 1.5 amps of load on the 5 volt, and we still have about the same ripple on the 5 volt line. That's perfectly acceptable. Now let's have a look at what the 12 volt line looks like. Here we have our 12 volts showing on the oscilloscope. We have 100 millivolts per division, and the total amplitude of the ripple here is about 50 millivolts. This is perfectly fine. This is a good working power supply, and it's a stark contrast to the first one that we tested. So I'll be testing this Omega 600 with this Omega 500 power supply. Our next step is to do sort of a pre-flight inspection before trying to power up the board. We want to look for obvious signs that things are wrong. It may be leaking capacitors, missing components, bent pins on components, things like that. There are a few things which might throw you off though. Some older circuit boards will have a wrinkly appearance to them. This is perfectly normal and just has to do with the way they are manufactured. Also, some ceramic disc capacitors have a waxy appearance to them. This is also perfectly normal and it's nothing to worry about. This type of capacitor rarely fails. There are types of capacitors that tend to fail over time. One is the wet electrolytic shown here. It can bulge from the top or the bottom, and it can leak, in which case you'll see a wet corrosive substance on the circuit board, which sort of smells like fish. Another type of electrolytic capacitor is the tantalum. These tend to fail in the short circuit manner, and they'll get this charred appearance and can sometimes pop, just like popcorn. In this case, I notice that the ROM chip does not take up all the pins in the socket, and that's perfectly normal for this case. This board was made to work with different size ROMs, so this is okay. Looking at all these electrolytic capacitors, I can see what might be a little bit of leakage around some of these. And from the research I've done, this does seem to be a common fault on the Omega 600, so this is something to keep an eye out for. Other than those couple things, everything looks okay on this board. There is nothing that looks burnt or broken, and we have all the parts. I did notice down here on the bottom, this is a revision 1.3, so that is the schematics that I've looked up. One last thing we want to do before we try to power this board up is to check the power rails to make sure that they're not shorted. Now, on some boards they might use tantalum capacitors, and those are famous for failing shorted. And if you apply power when they're in a shorted state, they tend to pop like popcorn. So in an abundance of caution and to keep us from further damaging the board, it's an easy matter to check those power rails first with an ohm meter. We'll go ahead and do that now. Of course, the method you use to test the power rails depends on the machine you're working on. For instance, I know from looking at the schematics that this floppy drive connector right here has 2 ground pins in the middle, and this is 5 volts and this is 12 volts. So this gives us an easy way to test those 2 rails. And if I go from ground here to 5 volts, the meter shows around 100 ohms, and I don't know exactly what that should be, but that's not a short circuit, so it's okay. And then we'll do the same thing on the 12 volt side. That's showing in the megohm range after a while, so that probably means we charged up the capacitor and there's nothing else on that 12 volts that's really drawing a lot of current. Again, it's not shorted, so it's okay. Another way to do it in this case is right at the power supply connector. And I know from looking at the power supply connector pinout that the center pin is minus 12 volts, which is one I have not checked yet. So I'll find a ground here on a ground plane. That right there. And this should be the center pin. And we don't have a short there either. So that's okay. Now we're finally at the point where we can apply power and be reasonably assured that we're not going to further damage the computer by doing so. What we want to do at this stage is notice what happens. Do we get garbage on the screen? Do we still have a black screen? Are there any visible or auditory signs of life at all? Now in this case, I don't have the sound hooked up. And I have a bit of an advantage because the owner was nice enough to send me this email, and it said he did notice that there was a black screen, but his monitor acted like it was getting a signal. So I've got the power hooked up, I've got the video hooked up. Let's go ahead and turn on the power. And we get nothing on the screen, but my Extron converter box is telling me that it does have an input, and it's an RGB input. So this is at least generating some sort of signal, but we just don't know what it's doing yet. Depending on how you have your computer hooked up to your monitor, the monitor might have some built-in functionality that'll tell you that a video signal is present, even if there's nothing to that video signal. Even if it's displaying a black screen, it'll say, hey, there is some sort of video signal here. And that is a big clue. Another thing you can do when you have a black screen to see if it's just a display problem, but the rest of the computer is working okay, is to try to blind type in a command. For instance, on a Commodore 64, you could try to load a program from the cassette. If the cassette starts turning, then you know that at least part of the computer is functional. Of course, these tricks are completely dependent upon the particular computer you're working on, so you'll have to hit up the forums and other owners to find out what you might be able to use in that case. Another thing we can do at this point is check on the board to make sure the power is getting from the power inlet through the filtering circuitry and to the rest of the board. We already found out that this pin on this connector was 5 volts and this was 12 volts, so I'm going to hit a ground pad on the corner here. And I've got my meter set on volts, and I'll very carefully touch that pin, and I see 5 volts there, and I see 12 volts there. So this looks like we're in pretty good shape. Now the minus 12 volts is really only used for the audio generation circuitry, I think, so I'm not terribly worried about that at this point. On some computers like a Commodore 64, there's a couple extra power supplies built into the circuit board that we would need to check at this time, but we can get into those later. At this point, we've powered up the computer, and we know that we have the proper voltages on the board, and there seems to be some sort of video output, although it's a black screen. The next thing I like to do is check the clock signal. When working on things like this, I like to print out the relevant page from the service manual and make my own notations on here, and I put these in a file, and when I work on the same computer again, I can go back and reference that. The clock is generated by a crystal like this, or a crystal resonator like this. The difference is the crystal is just a raw piece of crystal in a can, and there's some other supporting circuitry around it to make it oscillate. And a crystal resonator has a lot of that circuitry already built into it. This crystal just has to do with the composite video generation, so we're not going to worry about it too much at this point. This crystal oscillator, on the other hand, is the main system clock. It goes through some components here in this IC and goes up to pin 34 on the Agnes chip. Now the Agnes chip is marked at pin 1 right here on this side in the center, and if you count around, you'll get to pin 34. And you can just see, if you look really closely at the traces, it goes to a little resistor there and then on down to this chip. Now I've got the oscilloscope set up so we can both see what's going on. You could also use a logic probe for this type of test. And I'll try not to get my mustache in the shot here while I very carefully test right there on that pin. And we do have a clock signal about 28 megahertz, which is correct. Now our Agnes chip takes that 28 megahertz clock in and it divides it up into several different clocks out. One of those is on pin 37, so we'll go ahead and check that really fast. And there's a clock out. So we know that our Agnes is doing something. The system clock sort of acts like the bass drummer in a marching band. It keeps everything else in time. Now that we know our clock generation seems okay, the next thing I like to move on to is the reset circuitry. That's over in this section of the board. And the Amiga 600 uses the good old 555 timer chip. So we want to look at pin 3 on the output of the 555 timer. The scope is set to a 500 millisecond per division time base. You can see how slow it's moving across the screen. That'll let us see the reset pulse really easily. Turn it on. The reset pulse goes high and then back low. So we know the 555 timer is generating that pulse. And we can go over to another one of the chips to make sure it's actually being sent across the board. So now we're over on the reset line where it enters the Agnes, and when I turn power on, we can see it stays low and then jumps up high. So it does look like the reset circuitry is working properly. We now know that we have the proper voltages on the board. We have a clock signal, and our reset signal is functioning. What I like to do next is check for activity on the address and data lines. This will give us some indication that the processor is doing something, even if it's not the right thing. On this particular board, the easiest place to check the address and data lines is here on this ROM chip. We're not concerned with exactly what activity is on each of these pins. We just want to see if they're doing something. So we can check these one at a time. You can see there is activity, so it looks like the processor is doing something. And when you go down the line here, and you find a pin that's not doing anything, that seems stuck, take note of the voltage level. I've done this already. And I made a little notation here, and I checked that against the schematic to see what those pins did. And some of them were power input, and some were other signals that should be in a fixed state, so that was fine. At this point, I was kind of puzzled because I needed to study the schematic a little more to try to find a direction of where to go. Now that we know the processor is doing something and that the board is trying to put out some sort of video signal, I thought the next place to check was some of the video output signals. There's a couple buffer chips up here. We can check on all these resistors. These are the data lines for the various colors, and we can see that for the most part they're doing something. I was a bit confused at this point because it seemed like the board was indeed trying to output a video signal, but I wasn't seeing anything on the monitor. And then I thought, well, what if this happens to be a PAL machine? And I know some of you have been screaming this at me for this whole video, that this crystal that I pointed out before was only for the composite output chip is only here on PAL machines. And sure enough, if we look at the Agnes part number, it indicates that it's a PAL Agnes. And I thought, well, maybe the owner didn't realize it was a PAL computer and he didn't have a monitor or upscaler that could handle the 50 Hertz output. But my Extron scaler should be able to handle that. So I kind of poked around on the settings of my Extron scaler, and while doing that, I noticed that silly me, in the course of moving and straightening some things around a few weeks ago, I had left the VGA output cable unplugged. So once I plugged that in, I did have a video signal output from this computer. And so I thought, well, I'll contact the owner and check to see if he knew it was a PAL machine. I heard back from him this morning, and he did. So he's got another computer that's a PAL, which works with his monitor and upscaler. So there is some inherent problem on this board, and it just happens to be working now, which is a very difficult thing to troubleshoot. So here you can see the output we got, and it's rather wonky. The colors are off. It's rather blurry. So there is something wrong. And I went ahead and I hooked up the composite output to input 1 on the Extron. And you can see right now it's completely black, but when I first turned it on, there was a picture, but it was also very bad. And if I played around with the capacitors over by that composite output chip, it caused the signal to flicker in and out. Now you might be saying, hey Bert, didn't we kind of take the long way around just to get back to where we were at the beginning, knowing we needed to replace the leaky caps? Well, that's a fair point. My goal for this video was to introduce a systematic approach to troubleshooting, which will help get us on the right track to completing the repair. By checking the functionality of fundamental subsystems, we are able to determine that the computer seemed to be trying to output a video signal, although we were getting a black screen, the same as what the owner reported. Knowing that it seemed to be generating a video signal led us to the unplugged cable on the Extron video scaler, and thankfully we didn't get led too far down the primrose path. Once that VGA cable was plugged in and the display verified, although it's not a very good display, we were able to move on and do another test using the composite output, and found that it was a bit flaky, especially if we pushed on the area of the board near the capacitors around the composite video generation chip. All of this pointed us back toward the leaking capacitors that we saw in the visual inspection. However, now we have more data to verify that suspicion, even though the display is now working where it didn't work for the owner. This circuit board will now get a good cleaning and a recapping, and then some further testing to verify its functionality. In this episode, we covered the initial evaluation of a vintage computer and the steps used to try to get us on the right path to finding and repairing the failure at hand. These basic steps are important to keep us from replacing parts that don't need to be replaced and potentially causing more damage to the circuit board. It really pains me to read on a forum or Facebook group that somebody's replaced a lot of the ICs on their computer and they still can't get it to work. I hope that by sharing these troubleshooting techniques, I can save others a bit of frustration when they're working on their vintage computers. I've put a tentative list of topics for this video series in the description down below. Please have a look at that and let me know in the comments section what you think. If you'd like to see more videos like this and want to help support the Hey Birt channel, look in the description below for the links to our Patreon and Subscribestar accounts. Your support is appreciated. Say, if you're a subscriber, thanks. I really appreciate it. It helps out a lot. If you're not, what the heck are you waiting for? If you look down below, you'll see a rectangular subscribe button. If you click on that dude, it'll subscribe you to the channel. After you've subscribed, look for that bell-shaped icon and click on that. That way YouTube would be nice enough to let you know just as soon as I post a new video. Also, we just passed 1,000 subscribers. That's a really big milestone on YouTube, and I'd like to thank you from the bottom of my heart for your support. It's really appreciated. Until next time, bye.